Okay, in differentiation we learned some concepts first. We learned that the differentiation is the rate of change of a function. For example, we learned that a function like this would have a rate of change which is has high value. A function like this would have a rate of change with a low value. Okay, a function which is like this is a high rate of change. It changes quickly, but it decreases. So it has a high value, but a high negative value. Okay, it has a sign which is negative. This is a positive change, and this is a negative change. So we may have also a low a rate of change which is low, which has a low value, but it is negative. Why it is negative? Because it is decreasing. So it has a low value but negative. Okay, so I've learned that dy by dx, which is exactly the rate of change and which is exactly the slope of tangent. All of these are all equivalent definitions for the same concept: the rate of change, the differentiation, the derivative, the rate of slope of tangent. We learned that it has a value and it has a sign. The value corresponds to the rate of change itself, and the sign corresponds to its direction, whether it is increasing or decreasing. Okay, and we also learned that we have a table of differentiation. We have for every elementary function that we have studied, we know that its derivative. For example, we learned that x power n, its derivative is n x power n minus 1. And for example, for the exponential function, the derivative is as it is. It is the same exponential. For a power x, whenever we have a base which is different from e, the derivative will be the same function, but we multiply it by the len of the base that took the place of e. So we multiply it by len of a. Okay. Also, we learned that the derivative of len x, what is the derivative of len x? It is 1 over what is inside it, which is 1 over x. What about log base a of x? We learned len x. What about log base a of x? If you remember, we studied before that we can relate log to the base a of x to the len x by this relation. It is just len x over len a. So by that rule, we can find the derivative. The derivative would be 1 over x and divided by len a. Okay, so that is how we that was the table of differentiation. This aside. That was the table of differentiation, and we also learned some rules for differentiation. For example, we learned the rule of linearity, which is the derivative of c1 f of x plus c2 g of x. It is just, this can be distributed as if it was a number. So it is distributed. This is called the linearity property. And it is not general. Some students may think that they may, for example, if I had, for example, len of two terms like this, can I distribute the len? Could I distribute that len to be len of that plus len of that? No, this cannot. This is formidable. I cannot do that. Why? Because len is non-linear. Okay, so what is a linear function? A linear function is, or a linear operator, it is an operator that can be distributed just like numbers. We know that if we have some numbers like this, we can distribute it. Okay, so what is a linear operator? A linear operator which has this property. And in general, functions and operators are not linear, or non-linear. For example, we learned that sine of two angles is not the sum of the sine of these two angles. So This is, for example, this is formidable. I cannot distribute a function or an operator in general on the summation, okay? But some operators like this, the operator of the differentiation, can be distributed like this, and that's why we call this operator a linear operator. We call it as the linear property, which we can distribute it like this to be d by dx of c1 f of x plus the derivative of c2 g of x. Then after distributing, we can also take the constant out of that, so it would be c1 d by dx of f of x plus c2 d by dx of g of x. So that was the first rule. Then we learned some other rules like the product rule. If you remember, the derivative of f of x times g of x, we learned that that would be the first derivative of the second plus the derivative of the first times the second. Okay, that was called the product rule. And we also learned the quotient rule for d by dx of f divided by g of x. So can you remember what was the rule here? We square the denominator, so it would be g of x all squared, and we differentiate the numerator, so f of x like the f dash of x, like that. Then we complete the numerator just like the rule of the product rule, but with a negative sign instead of a positive sign. So f dash of g of x minus g dash of f of x times f of x. Okay, so that was the quotient rule. Also we learned an important property, which is for composition of functions. When I have a function inside another function, whenever I have a function inside another function, that is called the chain rule. That is called the chain rule. What is the chain rule? If I need to find the derivative of that expression, we just find it by what is the derivative is just f dash. If I had this to be y, what is y dash? It will be the derivative of the outer function, which is f dash, and keep what is inside it as it is. I just make the derivative of the outer function, then I keep what is inside it as it is, then I multiply by the derivative of what is inside. So it is just like that. Okay, and we learned how to apply these rules. For example, if I had this function ln of sine of x squared plus 1, and I need to find the derivative of that function. What is the outer function here? It is ln. That is ln. That is the outer function. What is the derivative of ln? It is 1 over what is inside it. 1 over what is inside it. So it is sine x squared plus 1. So I finished the ln. Then I go inside the ln. What is the outer function that I will find? What is the first outer function? It is sine. What is the derivative of sine? It is cosine. Then I keep what is inside it as it is. So I finished the sine. Then I go inside the sine. I will find x squared plus 1, and that gives me two terms. One is the derivative of 2x, which is x squared, which is 2x, and the derivative of 1 is 0. So that is how we apply the chain rule in a condition like this. Also, for example, if I had this function y is equal to e power 1 over ln x cubed. First, when we find a ln, before making any derivatives on a function, a given function, we try to simplify it as much as possible. For example, if I find this ln, can we simplify this expression ln x cubed? Yes, we have this cube. We learned that ln x cubed, it is just 3x, 3 ln x. So I would re-express that function to be e power 1 over 3 ln x. So that is a better expression than that one. Okay, so let's find the derivative of that function. What is the outer function here? It is the exponential. What is the derivative of exponential? It is as it is. So I will just write it again as it is. So I finished the exponential. Then I go inside the exponential, I find this function. What is the first outer function that I will encounter here? It is 1 over. If you remember that expression, it is just 3 ln x. It is just like as if was like a bracket, all power negative 1. So the outer function here, it is the power of negative 1. What is the derivative of 1 over something, or bracket power negative 1? What is its derivative? It is negative power negative 2, which is, it is memorized as minus 1 over the denominator squared, and times the derivative of what is inside it. So what is the first function that I will counter in this expression? It is 1 over or power negative 1, or power negative 1. So what is the derivative of 1 over? It is minus 1 over squaring what is inside it. So it will be 3 squared ln squared of x. Okay, so that is an expression. What is the derivative of 1 over something? It is negative 1 over squaring of that expression. So now I have just finished the 1 over, the derivative of 1 over. Then I go inside it. What is inside the 1 over? I will just find this expression. So I will multiply by the derivative of that expression, which is 3 ln x. What is the derivative of ln x? It is just 1 over x. Okay, so that is how we find a derivative, or how we apply the chain rule in such condition. There is a concept that we need to make a note about it. For example, if I had f of x equal to cosine 2x, okay, and I need to find f dash of x squared, and I also need to find f of x squared all dash. So what is the difference between these two expressions? F dash of x squared and f of x squared all dash. What is the difference? Now, if you look at that expression, I need you to remember that f dash is a function, and every function is defined by how it operates on its input. So when I have f of x, what I'm telling you in this expression, it is how f operates on its input. I tell you that f operates on its inputs by taking the cosine of double the input. Okay, so that is just an explanation of how f operates on its input. So that is that also happens for f dash. When I tell you that f dash of x, for example, for this function, it is just negative 2 sine 2x. That is the derivative of that function. So f dash is also a function, and this is how f dash operates on its input. So f dash operates on its input in this way. It takes minus 2 sine 2x. So when I tell you I need to find f dash of x squared, how would I find this expression? I just find how f dash operates on its input, like this expression. I tell you how f dash operates on any input such as x. Then I find how it operates on x squared afterwards. So I will operate f dash on x squared, which means that I will take every x in this expression and put x squared instead of it. So the result of that will be minus 2 sine 2x squared. That is the result of that expression. And that's why when I tell you I need to find f dash of pi, for example, f dash of pi, for example, do I first apply f dash of pi, then I make the derivative? No. We first find the f dash. We first find how to find this value. We first find f dash, then afterwards we apply x to be pi. So that is how f dash operates on that pi. I first find how f dash operates on any x, then I find or apply x to be pi. So what would that expression be in this case? F of x squared all dash. Yes, in this case we find f of x squared first, then afterwards we make the derivative. So in this expression, what is f of x squared? We apply f on x squared, f on x squared. So it would be cosine to x squared all dash. We need to find the derivative of that expression. And in that expression, we will need to apply the chain rule. So that will be minus sine of 2x squared multiplied by the derivative of what is inside, which is 4x. Okay? So the result of that expression, that these two expressions are different from each other, and we need to differentiate between them. Okay? We'll learn today another kind of differentiation, which is called implicit differentiation. Implicit differentiation. This is when I find an implicit relation between x and y. For example, if I had this expression, y squared plus x squared y power 5 plus 6 over y equal to 7 sine y over x. That is called an implicit relation between x and y. This is called an implicit relation between x and y. What is an implicit relation? It is the opposite of an explicit relation. What is an explicit relation? An explicit relation, when I tell you that y is equal to some function of x, it is obvious here. On one side we put the y, and on the other side we put all the x's. But in this relation, it is an implicit relation because x and y's are all mixed with each other in the expression. So that is an explicit relation. That is an explicit relation between x and y, and this is an implicit relation between x and y. Okay? Now, all of the examples that we have encountered before, we had an explicit relation for x and y. Take a chair and put it here. In all of the examples we have studied, we encountered only explicit relation. I would find only y on a side, and the x's are all on the other side. But how to deal with an expression like this? Should I first, to find y dash for this relation, to find y dash for this relation, should I first write it explicitly y equal to some function of x? No, I don't need to make that step, and I just find y dash by implicit differentiation. So what is implicit differentiation? It is very simple. All you have to do is to differentiate both sides as if y is a function of x. You just make differentiation both sides as if y is a function of x. So if I need to find the derivative of y squared, how would I differentiate y squared? Now I know now that this is a function of x, so it is just like as if I have a bracket all squared. So how would you differentiate a bracket all squared? You take the power down, then you subtract 1 from the power, then you multiply by the derivative of that bracket. Okay, so that is exactly that I will do in this expression. To find the derivative of y squared, the first function that we encounter is that squared. What is the derivative of squared? It is 2 of the bracket power 1. Okay, times the derivative of what is inside the bracket, which is y. I will call it y dash. I just know that there is some function y, there is an expression in x, but I don't know that expression, exactly that expression. So I just write it as y dash. Okay, so that is the derivative of that term. What about this term? Now this, I will consider this to be as a product between two functions of x. So that is x squared, and that is a function of x all power 5. So I will deal with it with the product rule. I will deal with it as a product rule. Apply the product rule in that term. So it is the first function times the derivative of the second, which is 5. I take the power down, y power 4, that I finished the power 5. Then I multiply by the derivative of what is inside, which is y dash. Okay? That is the first term in the product rule. For the second term, I differentiate the first expression, which is 2x times the second as it is. So these are the two terms of the product rule for this term. Okay, then I continue. 6 over y, I've learned that the derivative of 1 over something is just minus 1 over that square times the derivative of what is inside that thing. So that is exactly that expression. So it will be minus 6. It will just be minus 6. The derivative will be minus 6 over the square of the denominator. But I remember to multiply by the derivative of what is inside. So that will be, what is the derivative of that y? It is y dash. Remember, you deal with that function, not this. When I tell you, some students make a mistake to multiply by the derivative of all of that. No, I multiply by, every time I look on the original function, not the function that I'm putting my the terms of the derivative function. I'm just looking at the original function, not the, whenever I do the steps of the differentiation, in every step I look on the original function, not the derivative. Okay, so now I've just finished that side. I will just say that this is equal to the derivative of the other side, which is 7, and in this case I will use the quotient rule, which is the square of the denominator. Then I differentiate the numerator, which is cosine y. Is it cosine y only? What is the derivative of the numerator? Is it cosine y? Multiplied by, I finish the sign. Then I go inside it to multiply by the derivative of what is inside it. So it's y dash. So that is the derivative of the numerator times the denominator as it is, minus the derivative of the denominator, which is 1, times the numerator as it is, which is sine y. Okay, so now I have just finished the differentiation operation, or the differentiation step. There is still another step that I need to make, which is to find y dash in one side. I need to find y dash in one side. How to do that? I will just take that y dash and find all the terms, including that y dash. I'll find this term, and this term also, and also this term, and this term also. Okay, so I have all of these terms. I need them to be with as a coefficient to y dash. So let's make that. In this term, the coefficient will be to y. In this term, it will just be 5x squared y power 4. So, and for this term, it will just be minus 6 over y squared. For this term, what is the coefficient? It will be, I'll just take it to the other side, so it will be with a negative sign. Okay, now we have 7x cosine y all divided by x squared. Okay, I've just taken all the coefficient of y dash in this case. Okay, now I've just taken every term with y dash, and I took it as a common factor. I took y dash as a common factor. Now, every term that doesn't contain y dash, I take it to the other side. I'll just take it to the other side. So that's why this term, for example, this term would be taken to the other side. It would just be minus 2y power 5. Also in this side we have this term which doesn't contain a y dash, so it will be 7 minus 7 sine y over x squared. So afterwards I just need to find y dash. Y dash would be, I may symbolize this as 1 and symbolize that side as 2, so the derivative would be 2 over 1. The derivative would be that expression divided by all that expression. Okay, so that is how we applied the implicit differentiation. Okay, let's apply that again on another example. I need to find y dash for this implicit relation, sine y equals tanh y. So I will just apply the derivative both sides. So in the first term I will just find the product. So it is the first as it is times the derivative of the second, which is y dash. That is the derivative of y, it is y dash, plus the derivative of the first, which is 2x, times the second as it is. So these are the two terms of the product rule applied on the first term. For that term, sine, what is the derivative of sine? It is just cosine, and keep what is inside it as it is. So I finished the sine. Then I go inside it, I multiply by the derivative of what is inside it, which is y dash. Okay, so I finished that term. That is equal to tanh. Do you remember what is the derivative of tanh? It is sech squared of y. So that is the derivative of tanh. Then I go inside it. What is the derivative of y? It is just y dash. What is the next step? I take all of the y dashes in one side and take it as a common factor. So that's why y dash, there will be x squared, and there will be plus cosine y. So, and I also have this term, which is minus sech squared y. Okay, and all the other terms that doesn't contain a y dash, I'll just take it to the other side. So that will be minus 2xy. So what is y dash in this case? It will be minus 2xy over x squared plus cosine y minus sech squared y, like this. He may have asked me to find the slope of tangent, for example, at a point 1 and 1, for example. That point should be on that relation. If I give you some point, I'll just apply that point on that expression. I'll just put x to be 1 or any 2 points or any point, x node and y node. I just put x node for every x and y node for every y. Okay, so that is how we apply the implicit differentiation. For example, if I had this expression, z is equal to x cosine y ln x times y. If I need to find, and I told me to find z dash. He told me to find z dash, okay? And he told me that y is a function of x. Y is a function of x. So to find z dash, or d by d z dash, which is dz by dx, we just apply the rules as we have learned. Okay, this is a three functions multiplied by each other. How to deal with a product rule for 3 functions? We make the derivative of one and take the other two as they are. Then we change the position of the derivative and we keep the other two as they are. So for example, I would just make the derivative of that x, which would be 1, times the other two as they are, plus the x, I will take that x as it is, and that ln x and y as it is, and we'll just multiply by the derivative of cosine y, which is negative sine y times y dash. Then the third term would be take x as it is and cosine y as it is, then we multiply by the derivative of ln x times y. What is the derivative of ln x plus x times y? Before making the derivative, I know that I can simplify this expression. Whenever I have ln of a product, what is the ln of a product? It is just ln x plus ln y. So what is the derivative of that expression? It is just the derivative of that expression, which would be 1 over x plus the derivative of ln y, which is 1 over y, times the derivative of what is inside. So that is the derivative of z dash in this expression, knowing that y is a function of x. So what if I had this expression, for example, z is equal to y times y dash all squared, and I need to find z dash. I need to find z dash for that expression, and I know that y is a function of x. Now, for this expression, we also have a product rule. So it is the first as it is times the derivative of the second. What is the first thing that I encounter in that second function? It is the power 2. What is the derivative of power 2? It is 2, and take the bracket, and I subtract 1 from the power. Then I multiply by the derivative of what is inside the bracket. So what is the derivative of what is inside the bracket? I have a y dash inside the bracket. What is the derivative of y dash? It is y double dash, which is the second derivative. Okay? It is y double dash, which is the second derivative. So that is the first times the derivative of the second. Then I add up the derivative of the first, which is y dash, times the second as it is, which is y dash all squared. And I may further simplify that expression to be 2y dash y double dash plus y dash all cubed. Okay? So if you notice in the table of differentiation, you would notice that there is a whole category of functions that we didn't put in the table. We have studied all of these, and also the trigonometric and hyperbolic. There is a category in functions that we haven't put still we haven't put in the table. What do you think they are? They are the inverse trigonometric functions and inverse hyperbolic functions. For example, what is the derivative of sine inverse x? What is the derivative of sine inverse x? So why did we postpone putting that the inverse functions afterwards all the other functions? Because to make an expression for the derivative of inverse functions, we just apply the implicit differentiation. Okay? How would you do that? For example, if I had this expression y is equal to sine inverse x, we eliminate the inverse function by taking sine both sides. So that would be sine y equal to x. Then I would make our implicit differentiation, so that would be cosine y times y dash that is equal to 1. Then y dash will just be 1 over cosine y. And we learned before that y is just the sine inverse, so that will be cosine of sine inverse of x. So the derivative of the sine inverse function is cosine of sine inverse x. If you notice, look at this expression closely, you will find that cosine sine inverse x, we have studied the simplification of such an expression. Do you remember what were the steps to simplify that expression? When I have an inverse trigonometric function inside the trigonometric function, we make a triangle. For that we call it alpha, for example. We call that angle alpha, and the sine of that alpha is equal to x over 1. So that would be x over 1. Then I complete the triangle to just be 1 over x squared, root 1 of x squared. So what is the cosine of that alpha? It will just be 1 over the cosine of that alpha, it is just root 1 minus x squared. So that is exactly the derivative of the sine inverse. It is 1 over root 1 minus x squared, the derivative. And so we will include that rule in the table. We will include that rule in the table, and it is memorized. And so we could do the same steps for every inverse function. So let's make a general expression for the derivative of any inverse function. If I had, for example, y is equal to f inverse of x, like this. So let's eliminate the inverse function. I will take f for both sides, so it would be f of y equal to x. Then I make the derivative, so that will be f dash of y times the derivative of what is inside, which is y dash, all equal to 1. Okay? Then, so what is y dash? Y dash would just be equal to 1 over f dash of y. And what is y? It is just the inverse function. So y dash will just be equal to 1 over f dash of f inverse of x. So that is how we find the derivative of any inverse function. Okay? So that's why we will include these new functions to the table of differentiation. Let's put these rules. The sine inverse, its derivative is root 1 minus x, 1 over 1 minus x squared. The cosine, the tan inverse, its derivative is 1 over 1 plus x squared. The sec inverse, its derivative is 1 over x root x squared minus 1. So these are the three basic expressions, and there are other three which are the with the trigonometric functions with the For example, the cosine inverse and the cotan inverse and the cosec inverse. What is the derivative of these three with What are the derivatives? They are just the negative of these expressions. So that will be negative 1 over root 1 minus x squared, and that will be minus 1 over 1 plus x squared, and that will be minus 1 over x root x squared minus 1. Why is that? Because there is a relation between sine inverse and cosine inverse. That relation is that cosine inverse something is just pi over 2 minus the sine inverse of that thing. How would we find that, or how would we know that? That is just the equivalent expression for the relation that cosine of pi over 2 minus x is just or minus theta, it is just the sine of theta. Okay, that is a trigonometric rule. That is a known trigonometric rule that we have used before. Remember, we've used this expression in simplifying inverse functions. So the equivalent form for that relation in the inverse, it would just be in that form. So if you make a differentiation both sides, the derivative of pi over 2 is 0, and we have a negative sign which corresponds to that negative. And for each of these expressions, we have a similar relation like this. Okay? We also have, these are the inverse trigonometric functions. What about the inverse hyperbolic functions? We will also include them in the table. The inverse hyperbolic functions. That is sine inverse x and cosine. We learned that there are the three basic functions: sine inverse, cosine inverse, and tangent inverse. What are the derivatives of these three? The derivative of the sine inverse, it is 1 over, it is just like the sine inverse, but with changing the, instead of 1 minus x squared, it will just be 1 plus x squared. And for the tangent inverse, it is just like the derivative of the tan inverse, but with changing the sign, instead of plus, it will just be minus x squared. Okay, So for the rule of sine inverse is much like the rule of the sine inverse, but with changing the sine of x squared, and also for the tan inverse, it is just as if the rule of tan inverse, but with changing the sine of the x squared. For the cosine inverse, there is another expression which is 1 over root x squared minus 1. And that x squared here, because if you remember, I told you that the cosine is the largest among all the hyperbolic functions. So that's why it is, in this case, it is x squared minus 1, as if x is large in this case. As if x is large in this case, so I need to subtract 1 from that x. Okay? So these are the three basic function, inverse function. And if you remember, we have related these inverse functions to the len. There were some expressions that you need to know that relates these three to the len. For example, sine inverse is known to have this expression x plus root 1 x squared 1 plus x squared. So sine inverse is just like this expression. So whenever I encounter an expression like that, I know that this is just exactly sine inverse, and I know how to find the derivative of that expression instead of making lengthy operations or lengthy steps to find the derivative of that expression. Okay? So what about if I need to find the derivative of, for example, sec inverse of x? How would I find the derivative of sec inverse of x? Now, if you remember, we told you that even if you need to find, sec inverse. If I told you if you need to find, for example, sec inverse of some number, 2, for example, sec inverse 2, for example, how would I find the result in that in calculator? I will not find an expression like this in the calculator. So how would I deal with this situation? I just relate it to the three basic functions. These three are built in the calculator. Okay, these three functions are built in the calculator to find them. But sec inverse is not built in the calculator. So how would I deal with this situation? I will just relate the sec inverse. If you remember, we have taken before a relation which relates sec inverse to cosine inverse, which is exactly cosine inverse of 1 over x, or 1 over what is inside. Okay? So that is the relation between sec inverse, and it is not 1 over cosine inverse. I've told you that I don't take trigonometric relations and apply an inverse on them. No. Some of them they know that sec is just 1 over cosine. Then they apply an inverse on them. No, this is a wrong step. I don't make that mistake. Okay? Sec inverse of something is that it is just cosine inverse of 1 over that something. So whenever I need to find the derivative of sec inverse of something, I rewrite it in this expression, cosine inverse of 1 over that. Then I will find the derivative of that expression as usual. Okay? So for example, if I need to find the derivative of sec inverse of x, that is exactly cosine inverse of 1 over x. What is the derivative? The derivative would be, what is the derivative of cosine inverse? It is 1 over root what is inside it squared minus 1 times the derivative of what is inside it, which is minus 1 over x squared. Okay? So what is the derivative of, if I give you y is equal to tan inverse x squared? Remember, this is tan inverse, not tangent inverse. What is the derivative of that expression? It is, what is the derivative of tan inverse? It is 1 over 1 plus what is inside it squared. Remember, it is what would be what is inside it squared? It is just x power 4. Okay? Just remember that we take the derivative of a tan inverse, it is 1 over 1 plus what is inside it squared. So I finished the tan inverse, then I multiply it by the derivative of what is inside it, which is 2x. So that is the derivative of that expression. Okay? So we have learned, now we have learned the table and we extended the table. We have learned some rules, the linear rule and the product rule and the quotient rule and the chain rule. Then we will study another rule which is called the rule of function power function. The rule of function power function. So we have learned that if I had a function power constant, we learned to find the derivative of a function power constant. And we learned to find the derivative of a constant power function. But we hadn't studied how to find the derivative of a function power function. And that's what we will study in this case. So what was the derivative of a function power constant? What is the derivative of a function power constant? You just take that constant beside the function and take the bracket, write the bracket, the power -1, then I multiply by the derivative of that function, which is f dash of x. So that is how we find the derivative of a function power constant. What about finding the derivative of a constant power function? It is an exponential function. We put it as it is. But in this case, we have an a that took the place of e, so we will multiply by the ln of a. Then we go inside the function. We have finished the exponential. We go inside it, we'll find that f, so we multiply by f dash. Okay? So these are the two cases that we have studied before. So how would we deal with a function power function? For example, if I had y is equal to ln x all power sine x. Now, would I, in this case, would I take the sine beside the ln or not? Is it allowed to take the sign, allowed to simplify it? Would I simplify to take the sign beside the ln or not? No, this is not allowed in this case. This is different from this case. In this case, yes, I may say that this is sine x times ln x. Okay, this is correct. But in this case, this is a different situation. This is the power is on the whole ln. Here the power is on what is inside the ln. So in this case, yes, it is allowed to take that power down, but in this case not. Okay? So for this case, I need to find the derivative. What is the rule of a function? Now I've just noticed that this is just a function power function. A function power function. Neither this is constant nor this is a constant. So we have now a function power function. So what is the rule of finding the derivative of our function power function? We just apply that rule once and apply that rule once and add them up. Okay? So to find the derivative, we deal with that function as if it was a function power constant first. So we take the power down and put the bracket and subtract 1 like this times the derivative of what is inside the bracket, which is 1 over x. So I've just dealt with that function as if it is a function power constant. I've taken the power down, and for the bracket I've just made it sine x -1 and then multiplied by the derivative of that ln. Okay? Then I add up the other situation, which is deal with it as if it is a constant power function. What is the derivative of constant power function? It is as it is power sine x as it is, but take the ln of the number that have taken the place of e. So I multiply by ln of ln x. See this rule? I just multiply by the ln of a. So I'm taking the ln of the base. Okay? So now I have finished that function. I go inside it and multiply by the derivative of sine x, which is cosine x. So that is how we apply the rule of a function power function. We just deal with it as if it is a constant, a function power constant. Then we deal with it as if it is a function, a constant power function. Now, for example, if I had this function tan inverse x squared all power x cubed. So we need to find the derivative of that function. So I've just noticed that it is a function power function. So how would I find the derivative? I just deal with it once with as if it is a function power constant, and in another time I deal with it as if it is a constant power function. One, I deal with it as a function power constant and take the other case, which is constant power function, and add them up. So for the first case, I will just deal with it as if it is a function power constant. I will take the power down, put the bracket x cubed minus 1 times the derivative of what is inside the bracket. What is the first function that I will counter? It is tan inverse. What is the derivative of tan inverse? It is 1 over what is inside it squared. So it would be like this. Then I go inside the tan inverse, I will find the x squared, so I multiply by 2x. Okay? So this is the first case. Then I add it with the other case, which to deal with it as if it is a constant power function. A constant power function, in this case the derivative would be as it is times ln of the base times the derivative of the exponent, which is 3x squared. That is how we find the derivative of, in the case of a function, for a constant power function. If I had a situation like this, y is equal to ln x cubed tan power 4x over cubic root of x plus 1 e power x squared. And I need to find the derivative of that expression. So what is the derivative of ln? It is 1 over what is inside it. I will write all that in the denominator, then I multiply by the derivative of that denominator. Okay? But this is the long solution for that problem. Is there any other solution that I would do in this case? I've just taught you that if you find the ln, try to find any simplification that you do. Ln, I have here products and divisions, so I would make simplifications on this case. So I just apply the rules of the ln on that expression to simplify it before finding the derivative. So that will be, I will just write y as ln x cubed plus ln tan power 4x minus ln cubic root of x plus 1 minus ln e power x squared. Are there any further simplifications in this case? Yes, there are. I would take that power, take it down. Take that power, take it down. And that power, take it down. And that ln can cancel the e. So it can be, this expression may be further simplified to 3 ln x plus 4 ln tan x minus 1 over 3 ln x plus 1 minus x squared. So that is an expression for the same function which is much simpler from that one. So I will just apply the derivative on that simpler expression instead of that. Okay, so the derivative would be 3 over x plus 4 over tan x, the derivative times the derivative of tan x, which is just sec squared of x, minus 1 over 3 x plus 1 times 1 minus 2x. So that is the derivative of that function. If I've treated that function directly without making simplifications, it would take from me 2 pages to solve it. But making use of the ln and its simplifications have just simplified the solution as very much. So that's why they had made a new kind of differentiation called logarithmic differentiation. So noticing that power of ln in simplifying the function. Okay, so for example, if I had that y is equal to 3 power root x times the fifth root of 2x plus 1 e power x squared over sine power 5x squared sine inverse root x. Now this function doesn't contain a ln, so it cannot be simplified. It cannot be simplified. But what about introducing a ln to the problem to make use of the simplifications that the ln would make on that problem? So what about taking ln both sides? So I will introduce a ln to the problem to make the simplification, to make the problem simpler. So in this case, I will just simplify that expression to be ln 3 power root x plus, I will just apply the simplifications all directly. That would be root x ln 3 plus 1 over 5 ln 2x plus 1 plus x squared minus 5 ln sine x squared minus ln sine inverse root x. So that is ln y. Now that ln y is simpler than that expression. So that's why I can make a differentiation in this case, that 1 over y, the derivative of the left hand side, it is 1 over y times y dash, which we call it y dash over y. The derivative of ln is just y dash over y. Then I make the derivative of the other side, that is a constant. So that will be 1 ln 3, 1 over 2 root x, plus 1 over 5, 2x plus 1 times the derivative of what is inside the ln, which is 2, plus 2x minus 5 over what is inside the ln, which is sine x squared, times the derivative of what is inside the ln, which is just cosine x squared. Then times what is inside the sine, which is 2x. All of that minus sine inverse root x times the derivative of that sine inverse, which is 1 over root 1 minus what is inside it squared, which is x. So I've just finished the ln and I've just finished the sine inverse. I go inside it, I'll find the root x. So I will just multiply by 1 over 2 root x. So that is how we find the derivative of that expression. Then y dash, what is y dash? It is y times all that expression. Y dash, it is y times the whole that expression. So whenever I have a function like this, and it doesn't has a ln, but we introduced a ln from from ourselves that there was no len, but we have introduced a len for the function to make use of the simplifications that a len would make on the function. That is called logarithmic differentiation. So what is logarithmic differentiation? It is introducing of len. Yes, you take len both sides to the function to make it simpler so that I can make a derivative easily for the expression. Okay? There is also another kind of differentiation which is called parametric differentiation. What is parametric differentiation? This is the case, this is another expression for a curve, but relating the x and y to another third parameter. Okay, so whenever I have the x and y are both related to some parameter t or theta. This is, for example, we know the equation of a circle. It is x squared plus y squared equals r squared. Or for example, let's make it put as a number. That would be 9, for example. Okay, so we know that equation of that circle. So that is the condition that every point, the coordinates of every point x and y satisfy. There is another way to express the equation of the circle by using a parameter. For example, if I say x is equal to 3 cosine theta and y is equal to 3 sine theta. X is equal to 3 cosine theta and y is equal to 3 sine theta. If you take that expression, now if you make square for this and square of this and add them up, you will just get that equation. But what is the advantage of this expression? You are relating both of the x and y to some physical parameter or some other parameter, as if I move the theta, change the theta, whenever you are changing theta, the point is moving. The point is moving. So these you are relating both the coordinates x and y to only one parameter. Okay? So that's why we may encounter a condition where we have y is a function of some parameter t and x is also a function of some parameter t. Now we need to find the derivative of dy by dx. In this case, I have some expression like this and I need to find dy by dx. I can find dy by d theta, but what about dy by dx? In this case, to find dy by dx, you've just told me that dy by dx we can divide by d by dt for the denominator and the numerator. Okay, that is because y is a function that is a function of the parameter. That is the function of the parameter. So whenever I have a function expressed in terms of some parameter and I need to find the derivative of that function but with respect to another variable, how would I make that? I would just make the derivative to the parameter as usual, but divided by the derivative of that variable with respect to the parameter also. So, for example, if I had this expression, let's check it in this expression. So if I need to find dy by dx in this case, now dy, I told you I need to find dy by dx. I've just noticed that y is a function of theta. So what I would do in this case, I would find the derivative with respect to theta as usual. So that will be 3 cosine theta. But I divide by the derivative of x with respect to theta also. So that will be minus 3 sine theta. As if I have divided by d theta for the numerator and denominator. Okay? Now what if I need to find the second derivative? Now remember that this I can simplify it. If I need to find another derivative, we just simplify it before finding any derivative, so that will be minus cotangent of theta. Okay? So I have just learned that the derivative dy by dx, it is just minus cotangent theta. Okay. What if I need to find the second derivative? I need to find d2y by dx squared for this case. That is the derivative of the first derivative, which is minus cotangent theta. And I've just taught you that to find the derivative of a given function, that is the function of theta, I can find the derivative but with respect to theta, not with respect to x. So how would I deal with it? I will just make the derivative to theta and divide by the derivative of x to theta. Okay? So that's why to find the second derivative, in this case, the derivative of the first, that is the first derivative. That's what the first derivative, dx, dy by dx. Okay? So I will just, in the numerator, I will just find the derivative, but with respect to theta as usual. So that will be plus cosec squared theta. There is a minus, and the minus cancels the other minus, so it will be plus. Then I divide by dx by d theta, which is minus 3 sine theta. Okay, so that's how I would deal with an expression, parametric. This is called parametric differentiation. Okay, to find the derivative without the need to cancel the parameter from the two coordinates. Okay, I would have dealt with this expression or with this case by cancelling the theta first. I need to find dy by dx. So another one would cancel the theta between the equations. So in this case, for example, I would find that relation between x and y after cancellation of theta, or the parameter theta. Then I would find the y dash by using implicit differentiation in this case. That is the solution. But this is not always I will not always be capable to do that in every expression. Okay, the cancellation of the parameter is not always manageable, or I cannot do it in every case. Now, for example, let's take another example. If y is equal to t minus cosine 2t and x is equal to sine squared t, and he needs to find dy by dx and d2y by dx squared at t equal 3. Okay, now we have just noticed that you are relating the both coordinates x and y to t. Okay, now we need to find the first derivative, which is dy by dx, but I've just noted that y is a function of t. So how would I make that derivative? I would just might find the derivative, but with respect to t as usual. So that would be 1 minus or plus 2 sine 2t. But remember to divide it by the derivative of x with respect to t. So that would be 2 sine t cosine t. I've just made it as like this. Okay, so that is the first derivative. I'll just put t equal 3 in that expression. But I need also to find the second derivative. So how would I find the second derivative? I will just find the derivative of the first derivative. But before finding the derivative of that expression, let's simplify it. Whenever I need to find the derivative of some function, we simplify it first. So that will be 1 plus 2 sine 2x What is 2 sine cosine? It is sine double the angle. So in this case, that will just be cosec of 2t plus 2. That is a much simpler expression than that one. Okay, so let's find the derivative of the first derivative. That is the first derivative. Now this is a function of t, and I'm deriving with respect to x. So how would I encounter this problem? I just find the derivative with respect to t, but divide by dx by dt. So that's why I will just find the derivative of cosec 2t, which is minus cosec 2t times t times cotan 2t, divided by the derivative of dx by dt, which is 2 sine t cosine t, which I have just learned that this is just sine 2t. We may further simplify this expression. For example, this is cotan. I think this is minus 2 cosec 2 theta, and this is cotan divided by sine. I think there is some other simplifications. If you further simplify it, put the cosec as 1 over sine and put the cotan as cosine over sine, and so on. Okay, but I just did not to because I don't need to make another derivative, so I don't need to simplify it. I will just need to apply the point t equal 3 on that expression. Okay, let's take that example. So let's check that example. We need to find dz by dx. He's telling me that z is equal to y squared minus 2x squared plus 5 sine t, and he's giving me y is equal to ln t and x is equal to e power minus t. So he needs to find the dz by dx. I will just find the derivative as usual, dz by dx. So that would be 2y y dash, which is dy by dx. Okay, minus, what is the derivative of that expression? Minus 2x squared, which is minus 4x. What is the derivative of that? Which is plus 5 d by dx of sine t. Okay, but now we have, this is a function of t, and this is a function of t, and we need to find the derivative of this function of t with respect to x. So how would you do that? We just apply the parametric differentiation. That is 2y. What is the derivative of y with respect to x? We make the derivative of y with respect to t as usual, but divided by d by dt, dx by dt, which is 1 e power minus t. That is the derivative of dx by dt. Minus 4x plus 5. We have here a function of t, and we are finding the derivative but with respect to x. So how would I make this a derivative? I would just find the derivative with respect to t as usual, which is cosine t, but divide by dx by dt, which is minus e power minus t. Okay? Now if I had f of x is equal to sine t and y equal to sine nt, he's telling me to show that root 1 minus x squared y dash is equal to n cosine nt. So y dash, it is the derivative, so let's find y dash, dy by dx, which is y dash, which is the derivative of y, but y is a function of t, so we'll find it cosine nt times n. But I remember to divide by the derivative of x with respect to t, so that would be cosine t. So that is y dash. Now I would find that expression, that cosine t y dash is equal to n cosine nt, which is exactly what I am looking forward to prove, but we have this instead of that. So as if he needs me to express cosine t but in terms of x. So we know the relation between x and t, that x is equal to sine t. Okay? That means that sine t is equal to x. So that t, as if it has a triangle, sine t is equal to x over 1. When I complete the triangle, it would be like this. So what is cosine t in this case? Cosine t will just be the root of 1 minus x squared y dash, like this. So I've just proved the relation. Okay? Now from this relation we need to find another relation from root 1 minus x squared y dash equal to n cosine nt. Prove that 1 minus x squared y double dash minus xy dash plus n squared y is equal to 0. So let's take the derivative of that expression. Okay, I have that expression. We need to find the derivative of that expression. First we'll find here a product rule. So the first as it is, the derivative of the second plus the derivative of the first, which is 1 over both of double the root, times the derivative of what is inside the root, all times y dash. That is equal to, I am now deriving with respect to x. I'm finding the derivative of the derivative of x. So if I find the derivative of that expression, that would be minus n squared sine nt. Is that correct? No, this is a function of t and I am deriving with respect to x. That is the derivative, but with respect to t. I need to divide by the derivative of dx by dt, which was cosine t. So I need to divide by cosine t. Okay? And we have just learned that cosine t is just root 1 minus x squared when it is expressed with respect to x. Okay? So that's why for this expression, if you multiply the whole expression by 1 root 1 minus x squared, that would be 1 minus x squared y double dash minus, that 2 is cancelled with this one, so that would be minus xy dash equal to minus n squared sine nt. And that is exactly the expression. If you know that this is y, so that is exactly the expression that I need to prove. Minus n squared y is equal to 0. Okay? We will study some applications of derivatives. For example, to find the tangent line to a given curve. For example, if he tells me to find the equation of the tangent line to the curve y is equal to 3x squared minus 2 over x at the point x equals 1. To find an equation of a line, we need two parameters. We need to know the slope of that line, and we need to know a point. Whenever I have these two, I can find the equation of the line. So the point is given, which is x is equal to 1, but I need to know the point, the whole point. At x equals 1, at the point of tangency, we find that that point is belongs to the curve and to the tangent line. Okay, so that point belongs to the tangent line and the curve, to both the tangent line and the curve. So if I put to find the y coordinate of that point that the tangent line passed through, to find the y coordinate, I just apply that one on the curve. So that would be 3 minus 1, that would be also 1. So that is the point that I would need to find the equation of the straight line. What about the slope? How to find the slope of the straight line? It is just the derivative. Okay? It is just the derivative. So I need to find the derivative of that function at that point. Now we need to find the derivative. How will I find the derivative of that expression? Would I apply the quotient rule, or there is some simplification that I may do? Yes, I can simplify it before finding the derivative, which is 3x minus 2 over x. So y dash would be 3 minus, it would be plus 2 over x squared, like this. So that is y dash. And at x equals 1, what would be the result at x equals 1? Y dash in this case will be 3 plus 2 over 1, which is 5. So the slope is equal to 5. So now I know a straight line. I need to find the equation of the straight line which satisfies that its slope is 5 and pass it through the point 1 and 1. We know the general expression for a straight line is y is equal to mx plus c. M is known to be 5. So the equation is 5x plus c. And it passes, how would we find the c? From the point. The straight line, this tangent line must satisfy, the point must satisfy the equation of the straight line. So that's why we put the y is equal to 1 whenever I put x equal to 1. So that would be x plus 5. So that gives me that the c will be just equal to 4, minus 4. So that's why the tangent line equation will just be y is equal to 5x minus 4. 5x minus 4. So that is how we find the this is how we find the tangent line equation. Also, we have learned that the derivative is a rate of change. Derivative as a rate of change. And one of the most common applications of the derivative is when I have a position function x of t or s of t as a position function. What is a position function? For example, if I had a car like this, its position x, that is x, its position x may change with time. That position changes with time. Okay? So the velocity, what is the velocity? It is just the derivative of that x by dt. The velocity is just the derivative of that position function by dt. And what is acceleration? It is the derivative of the velocity, or it is the second derivative of the position. Okay? So, for example, if I give you this, if I told you that s of t, 3t squared plus 5, is a position function, where t is measured by second and s is by meters. Okay? So, he's telling me to find the velocity at t equals 10. He needs to find the velocity at t equals 10. How would I find the velocity? The velocity, it is just ds by dt. So that would just be 6t, like this. Then I apply at t equals 10. So that would be 60 meter per second. Then he's telling me to find the average velocity over the interval 10 to 10.1. What is the average velocity? The average velocity, if you are not looking in the details, you just look at the function at the car, how much distance that it have achieved, then divided by the time. Okay? It may have increased its speed at first, then it slowed down a little bit, then so on, but you don't look at these details. You just, to find the average velocity, you just find the achieved distance and divide it over the time. So that's why the average velocity, V average, it is just delta S by delta T. Okay, this is different from the concept of velocity. Velocity is an instantaneous. It is at a single instant. That is the velocity, like this. But this one, it is the average between, this is in an interval, in a given interval. The distance achieved in a certain interval divided by that interval. So that's why it is S2 minus S1 over T2 minus T1. T2 minus T1, it is obvious to be 0.1. S2 minus S1, S2 is the position at the instant T2, and S1 is the position at the instant T1. So I just apply for S2, I just apply 10.1 in this expression. So that would be 10.1, 10.1 squared plus 5. Then I subtract the S1, which is the S at T1, S at 10. So that would be 10 squared plus 5. Then I make that calculation, so that would give me 60.3 meter per second. And you may notice that when the interval is a small interval, it is 0.1. The length of the interval is just small. It is just 0.1 seconds. So the average velocity would just be approximate to the instantaneous velocity. Okay, that's enough for this